Now let's look at plane wave ansatz as a sense that far from sources, the wavefronts will become very large and they almost appear as planes. So let's look at plane wave ansatz. So I will put h bar mu nu of this plane wave form, in which we have this function where k is the wave propagation vector, 4 vector. It has a spatial part, which is just the normal wave vector, and the zero component, which is the frequency. Now, this spatial part is the normal vector to the wavefronts, that is constant phase surfaces, which are planes. And epsilon mu nu, this amplitude is a symmetric tensor. That is because h bar mu nu itself is symmetric, so this side should also be symmetric. So it's a symmetric tensor, and it's referred to as the polarization tensor. Now, one thing I would like to point out is that, as you can see, I'm using a complex notation. H bar mu nu was supposed to be a real field, but the right-hand side I've written something which is complex. That is because it is traditional when you study wave equations to use complexified field, and we usually declare the actual physical fluctuation to be the real part of this right-hand side. Now, the phase part of this, usually there is a phase part as well, that has been absorbed in this amplitude. So the amplitude itself is also complex. So epsilon mu nu, please bear in mind that this can be complex because it contains the phase part. And this is traditional when you study wave equation, especially if you remember your undergraduate physical optics class, in which, to simplify life, you switch to this complex notation, in which you have a complex amplitude and e to the I kx, which is the plane wave solution. So let's plug this in the wave equation. And when you take the box, when you act with the box operator, remember box will act on only the parts of h mu nu which contain x, which is its exponential function. And as you can see, because it's exponential, every time I take a derivative, it will pull down a factor of I k mu. So 2 factors it will pull down. You'll get an equation something like this: k squared times epsilon mu nu times this e to the I kx equal to 0. And of course, exponential function this is a phase; it cannot be 0. So, and epsilon, the amplitude can also not be 0 because then there is no wave if it is 0. So then the solution of this is that k squared must be 0, which is to say that this 4 vector k is actually light-like. So omega gets determined to be equal to the magnitude of the spatial part. Okay, so it's a light-like vector, and the frequency is equal to the magnitude of the free wave vector. In other words, gravitational waves propagate with the speed of light because omega by k gives you the speed, and this is equal to 1 because omega is equal to mod of k, so the speed is 1. So they propagate with the speed of light, gravitational waves. The Lorentz gauge condition, if I plug this plane wave ansatz into the Lorentz gauge condition, what I get is that epsilon mu nu, the polarization tensor, must satisfy this constraint. That is, contraction of the polarization tensor with the wave vector must vanish. So this will put a lot of constraint on what the polarization tensor can be. And let's not forget that we still have residual gauge redundancy because Lorentz gauge was not a complete gauge fix. We can still perform diffeomorphisms or general Fourier transformations with this parameter chi, such that it satisfies the wave equation, that is the harmonic function. If we do that, then we know that h bar mu nu will change by this. So I am writing this because I've only written the transformation of the metric perturbation, but not the transformation of the phase reversed metric perturbation. But here it is. So compared to the gauge transformation of the metric perturbation, you have an extra term, which is this. Okay. Now, because chi solves the wave equation, I can always write solution in the plane wave form as well. So this chi tilde is the amplitude, and just for future convenience, I've inserted an I here. Anyway, chi tilde is a complex amplitude, so it's fine if I put an I in front of it. And this is better because it will remove unnecessary factors of I in the future equations. Unfortunately, in Carroll's notes, he doesn't include a factor of I here, and as a result, in all equations involving the polarization tensor, he has extra factors of I hanging out. That's okay, but it looks unpleasant, so that is why I'm including an extra factor of I here in the chi tilde, so that in future equations we will not have unnecessary factors of I hanging out in equations. So, because it's a harmonic function, chi-nus are harmonic functions, we can always write them in the plane wave envelope form as well, with the amplitude being chi tilde nus. So this redundancy in description, that for the same physical gravitational wave you can write down two different metric perturbations or phase inverse metric perturbations, implies that the polarization tensor is also not unique. Each gravitational wave can be given by multiple different, infinitely different polarization tensors, which are related by this. So two of polarization epsilon and epsilon prime will give the same physical gravitational wave if epsilon prime is related to epsilon by this relation. So you have epsilon nu plus some extra stuff, and when you have this condition satisfied, then epsilon and epsilon prime represent the same physical wave. So there's a redundancy of description. Multiple polarization tensors represent the same physical gravitational wave. And this equation is completely analogous to plane waves in electromagnetism. If I write the plane wave solution, if I write solution in plane wave form, again we have a phase part and a complex amplitude, which we call the polarization vector instead of polarization tensor. And then the Maxwell equation again would imply that these are waves that traveling at the speed of light, so k squared is the light-like vector. And the Lorentz gauge will give you the condition that the dot product of the polarization vector with the wave vector must vanish. And as a result, this equation is a linear equation that can be quickly solved. The Lorentz gauge can be very easily solved. And the solutions are three solutions. In general, because epsilon can have four independent functions, you can have four independent solutions, but Lorentz gauge will kill one of them, so you're left with three independent solutions. Two of them are space-like vectors. As you can see, the time part is 0, so the temporal component is 0. So two of these solutions are purely space-like solutions, such that so the spatial parts are these three vectors, epsilon 1 and epsilon 2. I'm not sure if this is completely clear, but there are two kinds of epsilon. One is without the boldface, which is the 4 vector, and the ones with boldface, which are 3 vectors. So these are solutions to Lorentz gauge if this epsilon 1 and epsilon 2 3 vectors, they are orthogonal to the direction of propagation. And the final solution is, the third polarization is that epsilon can be k itself, because if I put k instead of epsilon here in this equation, it gives me this k square, which is automatically 0. So k also satisfies this Lorentz gauge conditions, and we get 3 independent solutions. Okay. We will take epsilon 1 and epsilon 2, these 3 vectors, to be such that epsilon 1, epsilon 2, and k hat, they form an orthonormal triad. You don't have to do this. We can take 2 spatial vectors which are both orthogonal to k hat, but in addition, I'm imposing the condition they are also orthogonal to themselves. I can always do that by choosing a right basis. Now, as I mentioned, we have residual gauge redundancy by harmonic functions. So A can be changed by gradient of a harmonic function. And that means that 2 polarization vectors which differ by multiple of k are the same physical electromagnetic waves. Okay. Epsilon prime, which is given by epsilon plus something which is proportional to k by this number chi tilde. Now, 2 such polarization vectors represent the same electromagnetic wave. Okay. So this can be used to show that this third polarization K is actually not there. It's not a physical polarization because it is gauge equivalent to the zero. Okay, so it's called pure gauge. Such kind of polarizations which are gauge equivalent to zero are called pure gauge. Okay, so they're equivalent to epsilon prime equal to zero. That's very easy to see because if you take epsilon to be the third polarization K, and if you choose this chi to be -1, then these two will cancel and you'll get epsilon prime to be 0. So this third polarization is gauge equivalent to 0. That means it is not there. It's not a physical field. So then we are left with just two physical polarizations. Okay, these are both transverse because they are orthogonal to the direction of propagation. Otherwise, they won't satisfy the Lorentz gauge condition. So these are the two transverse polarizations of the electromagnetic field, which is studied in undergrad. In fact, these are two linear polarizations which are orthogonal to the direction of propagation. These are transverse waves. This revision of electromagnetic waves is done so that we can exploit this when we write down the polarizations for gravitational waves. So this is the point. So you can use the Lorentz gauge polarization vectors for electromagnetic waves to determine the Lorentz gauge polarization tensors for the gravitational waves. The reason is that because these polarization vectors already satisfy the Lorentz gauge waves, then in terms of them, determining the gravitational wave polarizations will become easy. So in big D dimensions, we have D-2 transverse electromagnetic wave polarizations, which I mentioned before, and 4 dimensions we have done, there are only 2, but in big D dimensions, there'll be D-2 directions orthogonal to the direction of propagation, right? There'll be D-1 total space dimensions, and one of them is the direction of motion of the electromagnetic wave, and then orthogonal to that will be D-2 polarizations. These are denoted by this. So again, these are purely spatial, that is the temporal part is 0, and the spatial part is 3 vector, which is orthogonal to the direction of propagation. And there is D-2 of them. So this I index within the parentheses is a label. This is not a Lorentz index. This is a label to which one. And it can take values from 1 to D-2. They're all orthogonal. These spatial 3 vectors are all orthogonal to the direction of propagation. So the gravitational wave polarization satisfies the Lorentz gauge. I mean, we have chosen to work with the Lorentz gauge in which this equality must be satisfied. And we can write down the solutions in terms of these polarization vectors. So here is the solution. Okay. Here is the solution. So first class of solution, there are 4 different classes of solutions. The first class of solutions I'm calling epsilon mu with the label II, double I label. So this is a label, okay, and not an index or component. This is just a label like a name tag. On the other hand, mu and nu represent components. Okay, this is a tensor component. So please be careful. There are too many indices going around. So this II within the parentheses in all of these, in fact, represent labels or name tags. On the other hand, the mu-nus are components. So the first class has double I, where I can take many values, this label, and this is given by the product, outer product of the polarization vectors for electromagnetic waves with the same polarization, the same I. So automatically symmetric, because if I swap mu and nu, because the label I is the same, it remains unchanged. And as you can see, it's obvious that this will satisfy Lorentz gauge, because if I contract with K mu epsilon mu 0, so this vanishes. So automatically satisfies Lorentz gauge. Okay. Then the next class of solutions, class of polarizations, are in which I have the label IJ, and they're constructed like so. You take 2 photon polarizations with polarization labels I and J. It's I and J, and I is not equal to J, so they're distinct. And then you form the symmetric combination, mu and then you reverse I and j. So you can see if you swap mu and mu, these two terms get exchanged. That's all. So it's a symmetric combination. Okay. And here in the parentheses, I've indicated the number of such polarization centers. So because I can take d minus 2 different values, there is d minus 2 different polarizations in the first class. In the second class, I and j have to be different, and I and j each can take d minus 2 distinct values. Then the number of different such second class polarizations are d minus 2, choose 2, the binomial coefficient. Then the third class is when you take one of them to be a polarization vector, one of these EIs, and the other of them you take the k, the wave vector itself, okay, and you symmetrize it, which I have done here. And you can again check if I contract with k, this will vanish because epsilon is contracted with k vanishes, and k contracted with itself also vanishes. Okay, so this will vanish. And the last class is, which I have called epsilon mu 0, 0 label, is when you take just the product, outer product of two wave vectors, k mu, outer product of the wave vector with itself. Okay, k mu, k mu. And again, you can see if you contract with k mu, because of the fact that k mu is a light-like vector, this will vanish. And the number of such polarization is just one. We can only construct one polarization. Here it will again, for the third class, we will again have d minus 2 because there is this label I, and I can take d minus 2 independent values, distinct values. Alright, so how many are there in total? If you do the math, it will turn out, I'm going to leave it for you to do the math, but I'm going to tell you what's the answer. It turns out to be the number of polarizations turn out to be d times d minus 1 over 2, which is exactly what the number of independent solutions of the Lorentz gauge are. Remember, epsilon mu is a symmetric tensor, so it can take d times d plus 1 over 2 different values. And then the number of constraints on the Lorentz gauge is d, because as you can see in the Lorentz gauge, there is a free index nu which can take different values, so you have d different constraints, so you got to subtract, and you'll get the same number. Okay, so these are the full set of solutions of gravitational wave polarization satisfying the Lorentz gauge condition. We have to do a little more work because we know that Lorentz gauge is not a complete gauge fix. We have to eliminate more components or determine fix more components because symmetric perturbation otherwise it won't be uniquely determined. So we're going to do that by using the residual gauge dependency, which tells you that epsilon mu and epsilon mu plus this extra thing, they are the same physical gravitational wave. And for this chi tilde nu is an arbitrary, this is arbitrary. So these two polarizations represent the same physical gravitational wave. And by cleverly choosing this chi tildes, we're going to show that in particular these two, the last two, are actually gauge equivalent to zero polarization. So they're not physical, they do not exist. How do we do that? Well, let's consider the last case, which is equal to k mu, k mu. K mu. So then here we will have k mu, k mu. And it's very obvious if I choose chi mu to be I think there should be a minus on it. So if I choose this chi tilde to be minus half k mu, then that will cancel this k mu, and you'll get epsilon prime to be 0. Okay, so we have shown that this polarization is not there because it is gauge equivalent to 0 polarization. Similarly, you can show that I0 is also pure gauge. By starting with 0, we will take the 0 polarization and to it add this gauge transformation with the gauge parameter being epsilon mu I. Right? So these two terms will be there. The third term will vanish because k is proportional to, if I put chi tilde to be epsilon mu, that will vanish. So you'll get 0 plus something, and that something is exactly equal to the third class. Okay? So we have gauge transform the zero polarization into the third class. Because we have gauge transform from zero polarization, that means this is not a physical polarization, it is equal to 0. So we can get rid of them. Finally, you can use the gauge transformation with this gauge parameter and show that the first class, this, there are actually not d minus 2 but 1 less, because these are equivalent to these. Epsilon mu is gauge equivalent to epsilon mu minus this quantity, and this quantity, you can show that because of the subtraction, the number of independent components have now got reduced from d minus 2 to d minus 3. Why? So this is the gauge transform mu polarization. Starting from this, we can do the gauge transformation, we arrive here. If you add them, they will turn out to be 0. So there are d minus 2 polarizations to start with, and after gauge transformation, if I add them, their sum is 0. This is the idea of linear independence or dependence in vector spaces. If you have d minus 2 different vectors and their sum is 0, that means one of them can be determined in terms of the other. So the number of independent is going to be d minus 3. Okay, to get rid of one of these menu I. Okay. So let me just summarize what we did. We got rid of this last two by showing that they are gauge equivalent to zero polarization, and by gauge transformation we will eliminate two. We were able to eliminate one of the first class, so that's d minus 3. So we are left with d minus 3 of the first class and d minus 2 choose 2 from the second class. The second class is there. There's no way we can show them that they're gauge equivalent to 0, so they're physical. So the total number will now give you d times d minus 3 by 2. With the math there, a little bit. Yes. D minus 3 added to d minus 3 plus this d minus 2 choose 2. If you add them, you get d times d minus 3 over 2 polarization, each of which will satisfy these two conditions. That is, the zeros from the 0 I component will be all 0. It will be obvious, but please check. So the 0 I component, if I take the 0 and I, because polarization vectors have no temporal component, this will go to 0. And here also, if I take 0 and I, that is going to be happening. And then, of course, the trace, epsilon mu will be 0. Again, it should be obvious. If I take epsilon mu will give you the dot product of these two vectors, and we know we have chosen these to be orthogonal. So the dot product will vanish. So the trace of the epsilon contracted with this second class will vanish. Epsilon contracted with the first class will not vanish if we take it like that. But remember, the actual polarizations are these. If you contract with epsilon, then you can show that these will vanish. Okay. So if you contract with epsilon, this will give you 1. And then there are d minus 2 elements in the sum, each of which will contribute 1. So you get total d minus 2 divided by d minus 2. So 1 minus 1, that is again 0. Okay? So these two conditions are met. That means we are in transverse traceless gauge, which is the main gauge in which we write down the solutions to gravitational waves. Okay? Now, as I said, we should give special attention to the case d equals 4, because that happens to be our universe. And in that case, this accounting works out that d times d minus 3 by 2 is just 2. So we have two polarizations. So let's look at them. To do that, we first consider the electromagnetic wave, because remember, the gravitational wave polarizations are being constructed in terms of the EM wave polarization by taking two copies. There is a typo. This should be d equals 4. I'm sorry. So let's take the direction of propagation of the gravitational wave to be the z direction. Okay, so then the k mu takes this form. Okay, only the zth component and the time component were turned on. The xy component is 0 because we have chosen the direction of propagation of the wave to be the z direction. Then the two physical polarizations are the x and y, right? So epsilon 1 physical polarization is x, epsilon 2 is y hat, and then the direction of propagation is z hat. Another typo, this y should be boldface because it's a vector, 3 vector. Now from these, by taking outer products, we can construct the gravitational wave polarization. For example, let's consider the 1, 2 ij type. I can take two values here and j can take all the two values. So we will have just one combination, 1, 2, right? So this is given by this combination. And you can fill out this matrix by looking at various components. For example, let's look at the 0, 0 component. Right? If we consider the 0, 0 component, none of them have any temporal component, so this is the 0. In fact, it will turn out most of them are 0 except for the 1, 2 component and 2, 1 component. So they're interesting to look at. So let's look at the 1, 2. So mu is 1, mu is 2, 2, mu is 1, something like that. And from here, we can see this term is equal to 1 because the first component of this is 1 and the second component is also 1. This is 0 because we need the second component of the first vector, which is 0, and the first component. I'm sorry, this is the first component of the second component of the first vector and the first component of the second vector, that is both is 0, so this doesn't contribute. So you get 1, which is what I've done here. And similarly, because it's a symmetric tensor, 2, 1 component will also be 1. The rest of them are 0. Please do it by yourself once and check that indeed you get this matrix. So this, for reasons which will become obvious, when we proceed to the next couple of slides, is called the cross mode. Okay, with the cross. So off diagonal. And then the second polarization, which will be of this form. And there'll be only one of them because remember there are d minus 3 of these. Here d is 4, so there'll be only one such polarization, which is proportional to the difference. There's a factor of half here, but this pesky factor of half, there's no point carrying it around, so I've just removed it. So this is this combination. Okay, you can check, you can construct this yourself. You can put 1, 1, and here you'll have a sum over 1, 1, and 2. And there'll be a factor of half. If you do the cancellations properly, you get this with a factor of half, which I've dropped. So again, you can evaluate this and put the values in the matrix for different values of mu and u. In particular, this is the 1, 1 component. So let's see if this matches. 1, 1. So this is obviously the first polarization vector, which has the 1 component turned on. And for the second polarization vector, the 1 component is 0, so this will be contributing 0. Fine. And let's look at the 2, 2 component. So let's put 2 and 2. So this will contribute 0 now because the first polarization vector has no second component, while this has component 1 with a minus sign with a 0 or minus 1. Alright. So please, again, check yourself that this matrix is indeed what you get. And this is diagonal, except the diagonal values are 1 and minus 1. This is not sometimes, this is called to be the plus mode for reasons which will become obvious momentarily. So, of course, these are matrices, and it's important to get some intuition about what these represent physically. So, and which leads to the detection of gravitational waves. So we are interested in finding out more about physical effects on motion of test particles, which are impacted by gravitational waves. So if we have test particles, if the gravitational wave is impinging on them, what kind of physical effects on the motion will be produced? In particular, we will be focusing on the relative motion of test particles, okay? That is to say tidal effects, because we know gravitation manifests itself in terms of tidal effects. That means we have to study the GDZ equation with gravitational waves as a source. Okay, so we will consider slow-moving particles. Remember, gravitational waves are already derived in the weak field limit. Now, in addition, we are taking the slow-moving particles, that is, slow velocity. So we are in Newtonian regime, and we will see even in Newtonian regime, gravitational waves can be felt. This is how we observe gravitational waves. So moving particle means that the tangent vector, which gives the force velocity, I can take it to be this 1, 0, 0, almost zero velocity. And in such cases, proper time can be equated to lab frame time. Okay? And we're going to operate in the transverse traceless gauge. If you use this, then linearize with Riemann tensor, the component which is going to appear in the GDZ deviation is mu 0, rho 0, mu 0, 0. Because we are using in the slow-moving approximation. In that case, it turns out that the Riemann tensor is given by the second order time derivative of the metric rotation. Okay, or if you write in using plane waves, it's going to give you this double derivative in time is going to bring down two factors of omega. So let's write on the geodesic deviation. This is the geodesic deviation. Now, S is the separation of the geodesic deviation vector, and the left-hand side will simplify the two derivatives of time. The right-hand side, of course, has two factors of t and one factor of s, but because t is 1, we don't have them here. They are replaced by 1s, and we're going to have this, which I have written here. Okay, so this is the geodesic deviation in the Newtonian regime, and I've plugged in. This is the Newtonian regime. Now, it is evident that if z is the direction in which the gravitational wave is propagating, in the z direction, then the separation in the geodesic separation in the z direction will not be there. So, because the gravitational waves are transverse waves, not longitudinal component, it's kind of obvious. Because if this is 3, h will be 3, and we know from the polarization studies that epsilon mu for a wave going along the z direction has no 3 components. It only has 1 and 2 indices, non-zero components, and 1 and 2 indices are 1 and 2. So there will be no longitudinal component of the deviation, only the transverse. So S1 and S2 will not be 0. Okay, so let's do that. Let's take the plus mode. Maybe I'm talking about the plus mode, so this is diagonal, but the coefficients are 1 and minus 1. Components are 1 and minus 1. If I plug that in, of course, this is a matrix equation, but you can show that this implies this kind of an equation for the component S1 and S2. So the details, please refer to Carol. Does the algebra more in detail than what I'm doing, but this is a very simple linear equation, and you can convince yourself if you put the epsilon, what you should get is because of the plus mode, epsilon has 1 and minus 1 in the diagonal, so you get plus sign for the S1 component and minus sign for the S2 component. And these two can be easily solved because they are linear equations, double derivative in time, and this is the solution. Okay, so what you should notice is that the solution for the separation geodesics, S1 and S2, they have a fluctuating part, wave part, okay, this wave part, but this fluctuating parts exactly 180 degrees differing in phase because of the sign, plus and minus, so they're perfectly out of phase, okay, and Carol nicely described that if you consider a ring of particles, test particles, on which the gravitational wave is impacted in a direction orthogonal to the plane of the slides. So this is the gravitational wave. Then these particles, let's say the x direction, whenever it's going out or increasing, in the y direction they will be decreasing. So these test particles, and vice versa, when in x direction you have the gravitational wave squeezing them, in the y direction they'll get expanded. So they will oscillate like a plus sign. So that is why we call this the plus mode. So this ring of particles, when they oscillate, if you look, they will look like they're executing a motion like a plus. Okay. This also forms the basis for the LIGO experiment, which detected gravitational waves. What you had is, instead of this ring of particles, you had a Michelson interferometer forming the two directions S1 and S2. And initially, when there was no gravitational waves, they were balanced. So the light beams traversing in these two orthogonal directions, they had the exact same path length as a result of zero phase difference incident on this apparatus. What happens is that one of the arms gets shrunk and the others expand. As a result, the phase difference now becomes observable. And this is how the gravitational waves are observed, by looking at this kind of interferometer setup. You can repeat the same analysis for the cross mode. This is starting equation, and I'm sparing you the details, but please look at Carol's notes. He has the details. The algebra is there, and the solution is of this form. Now here you can see that the S1 solution mixes with the S2, and S2 mixes with S1. Okay. So again, if you consider a ring of particles, and I'm sparing the details here, but you can look at Carol, a lot of details are there. Then the motion will be in this kind of a 45-degree direction, and then these particles will move in this direction. So these ring of particles, if you observe them, they will execute a cross-like motion. Okay, cross-like motion. So that's why they call it cross mode. This mode of gravitational wave is called a cross mode. Again, you can set up a Michelson interferometer, in which these are the direction of the arms, and therefore, if these are of equal length, they will give you no phase difference. On the other hand, when the gravitational wave is incident on them, some of the arms will expand, the other direction will contract. As a result, you will get an observable phase difference. Okay, so this is how gravitational waves are detected using interferometers. Okay, that concludes today's lecture. And let's look at the summary and outlook. We considered the weak field limit of general relativity that is restricted to all our equations of leading order in the matter perturbation. It's called linearized GR. And it turned out that linearized GR is same as the Pierce-Pauli theory, which we learned in special relativity. Then we considered vacuum solutions, that is solutions outside sources. And these solutions are of the form of waves, gravitational waves. These are non-dispersive, transverse, and they propagate with the speed of light. In particular, we looked at gravitational plane waves, because far from sources, the wave fronts become almost like planes. And we constructed various polarization tensors for the gravitational waves in terms of polarization vectors of electromagnetic waves. Number of independent polarizations turned out to be d times d minus 2. And for d equals 4, there's only 2. And these two are called the plus mode and the cross mode. Next, we're going to look at gravitational radiation emitted from matter energy sources. Now we cannot consider them the plane waves, because near sources, the imprint of the geometric distribution of matter will be imprinted on the wave solution. So we will look at it in the next lecture. Thank you very much for your attention.